Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on sequences and series. And so far, we have looked at sequence accelerators, but now I'm going to look at some useful sequence operations that we can implement in Java. To remind you, we implemented sequences as a functional interface in Java, and then we added some default methods that do some transformations on the sequence, but we kept the identity of the sequence as an functional interface. And we also implemented default methods. So here these are default methods. We implemented some default methods for operator overloading for sequence interface: addition, subtraction, multiplication, and division. Okay, adding two sequences results in a new sequence which adds term by term. Subtracting two sequences just subtracts term by term and returns a new sequence. Multiplication, the same thing, multiply term by term. And division, you also divide term by term. And again, in order to keep the identity of the sequence as a functional interface, we add these as default methods. Okay, and then we can have some useful relations, and that are actually or particularly useful when we are dealing with perturbation theory using sequences. The first one is the definition of a sequence as the Kronecker delta. So delta of n, it's basically discrete signal or a sequence basically. So this kind of discrete signals occur, or we see them all the time when we are dealing with discrete systems, but here we looked at them as just sequences instead of a discrete signal. So a sequence delta, for n equals 0 it's 1, for n non-zero, for example -1, +1, -2, +2, etc., delta is 0. And then because this is a sequence by itself, we can just add it as a static method to the sequence interface. Okay, and then what I mean by that is that if we go back to Eclipse and look at our sequence project, we have this sequence interface, and it already has one public abstract method which is evaluate. That's our functional interface. And then we have other default methods for transporting the sequence: diff, Aitken, Shanks, Richardson, second order, third order, fourth order, and then operator overloading methods: sequence add, subtract, adding a number to a sequence. We define that as adding it to each term, so adding term by term. And then subtraction, multiplication, division, and then negation. Okay, so let's just quickly look at one example of this operator overloading. So let's create a test class, test operator overloading for sequence. I think we already looked at this operator overloading, but let's do that one more time to just remind you. So I'm going to call a method public static void test1, and here I'm going to create a sequence sec1, which is k goes, or n goes to let's say 2n, 2 times n. Okay, and I need to import sequence. All right, and then sequence sec2, I can say that just sec1 times sec1 plus or minus 1. Okay, and let's do a sysout sec1 evaluate at 1. So this should return 2 times 1, and then sec2, so sysout sec2 dot evaluate at 1. So this should return 2 times 2, which is 4 minus 1, 3. So we see that we do in fact get operator overloading. Okay, And again, because this is an interface, we're adding them as default methods, and all of them are public methods because the interface is public. So unlike classes that even if you define them as public, the method could be defined as private. For interfaces, if interfaces only have two access modifiers, it's either default access modifier or public. Default means it's a package level access, and public means it's open to the world. Okay, and then if you declare interface as public, all the methods are by default public and you cannot change it. So you see all these methods have this field green circle. In Eclipse it means it's a public method. And adding something like public abstract modifier to this, for example, to this method is unnecessary because it's implicit in the definition. Okay, so I cannot change any of these methods to private. It complains that illegal modifier for the interface method diff. Only public, abstract, default, static, and strict FP are permitted. So I cannot have a private method in a public interface. Okay, all right, so let's add some of the, so we have these transformations. Let's add the sequences, some of the operations. So I'm going to add a static sequence delta. It's going to return n goes to basically evaluate at n. Now this is complaining because cannot make a static reference to the non-static method evaluate. So basically what we need to do is we're going to return a sequence. So we're going to basically create a sequence, or maybe just return n goes, I'm going to use a multi-line lambda expression, and here I'm going to say that basically, or a single line. So if n is 0, so I'm going to use a ternary operation. If n is equal to 0, we're going to return 1 double, else we're going to return 0 double. Okay, and this is double, so remember, just note that I'm returning double. And let's go and test this. So let's create another test, public static void test2, and I'm going to invoke test2 to test the delta function. So sequence delta is sequence delta, and then sys out delta at 0, evaluate at 0, which is 1, evaluate at -2, which is 0, evaluate at 2, which is 0, so it's 0. So we have, now we have the so we have delta of n, right? The Dirac delta or the Kronecker delta of n. Now we can construct other sequences based on delta of n. For example, let's say I want to have a sequence an that is non-zero for n equals 0, 1, and 2, and it's 0 everywhere else. So I can say sequence sec, for example, and I can use the power of operator overloading, which is an absolutely beautiful thing to have. So I'm going to say, let's say a0 is 1, so 1 times delta of n, plus a1 is, let's say, -2, so I'm going to say, okay, now -2 times delta of n-1. So we want to also be able to shift the sequence. So let's say I want to have a sequence an, and I want to create new sequence bn, which is a shifted version, a n minus 1, for example. So let's go and add also this capability as a default method. So delta is one thing, but the first operator is shifting, so default sequence shift and int n m, for example. This shifts by m orders, m terms, so return n goes to basically evaluate at n minus m. Okay, so this is the very basic operation or transformation. We're shifting. Now I can say that let's test shifting. So let's say I want to create delta n minus 1. So this should be sequence delta shifted is delta shift by 1 plus 1. Okay, and now sys out delta shifted at 0. It should return 0. Yes, it returns 0, and at minus 1 it should return 0. At plus 1 it should return 1, because now we have delta minus 1 n minus 1, and delta is only 1 when the argument is 0, so n equals to 1 exactly, and 2 it should go back to 0. Okay, so this is how we shift a sequence, and then or we shifting or delaying a sequence. We can also call it delay. Maybe delay is a better terminology. Okay, so we have shifted delta, we tested this. Now I want to create a sequence just based on the delta. So delta takes care of the A0, and then delta shift by 1 takes care of A1 plus, let's say A2 is 5.1 times delta shift by 2. Now using operator overloading and basically the shift functionality or delay functionality, I created a new sequence. Let's do the sys out. So I know that asec, if I evaluate it at minus 1 and then 0 and then 1 and then 2 and then 3. Okay, so I should only get at minus only the only non-zero values are 0, 1, 2. So I get 0 at negative 1, 1 at 0, because we defined it as 1 times delta n, and then at 1 I get minus 2 because it's minus 2 delta n minus 1. So basically the definition of an is delta n plus or minus 2 or plus minus 2 times delta n minus 1 plus 5.1 times delta n minus 2. So you can construct any sequence from just the delta function. Alright, and this is a very basic fundamental concept in signals and systems when we are dealing with basically discrete systems. So 5.1 at 2 at 3 it's 0. Okay, all right. So now the next thing is so if I go back to our PowerPoint, so this is the Kronecker delta. We implement it as a static method, and using operator overloading and the shift functionality, we can do the construct any signal from delta. Okay, and the next one is unit step. Unit step defined at 0. A step at n equals 0 is 1 for n greater than or equal to 0. So we are including the equality in the 1, and then for -1, -n, n minus 1, minus 2, etc., it's going to be 0. So, and you probably can guess that un is the partial sum of delta n from 0 to n, okay? So again, we're going to use a static method, sequence unit step, and this is going to return n, again, lambda expression. We're going to test with 0, plus 1, other than that 0, 1. So returning double value. Just note that we're returning double because the sequence basically returns double. So if n is greater than 0, we're returning 1, otherwise we're returning 0. And then if I want to have a step at, let's say, n equals 2, so I'm 0 until n equals 2 and then jump up, I use unit step and then transform it using this shift functionality or delay functionality. Yeah. Maybe let's also add another method, delay. Maybe someone is more comfortable with delay, but they're basically the same thing, delay or shift. Okay. A delay is more suited for a discrete system because then the argument n is representing time steps, and n minus m is like delaying a discrete signal by m time steps. Okay. So for now, I'm going to just delete it, but if you're more comfortable with the delay function instead of shift function or shift terminology, just use delay. Okay, let's do public static void test3, and here, and let's invoke test3, and here we're going to create a sequence, step 0. So this is going to be a sequence stepping right at 0. Okay, so unit step by default is at 0, and we can also have another one that directly jumps at int m, and the way we're going to do it is if n greater than equal to m. But using this unit step with a delayed m and creating a unit step and 0 at 0 and then shifting by m is similar. Similarly, we can basically do the same thing, right? We can have a delta that gives us a delta at exactly m, right? So we don't need to use the shift functionality. So step 0, and then sysout step 0 evaluate at 2, for example. This should give us 1. At -1, this should give us 0. Yes, at 0, this should again give us 1 because we included 1 in the definition at 0. Okay. Now I'm going to basically create a new sequence, step 1, and take the step 0 and shift it by 3. Okay, and what happens here is that now this is basically a unit step at n minus 3. This was originally it's a unit step at n. So at 1, the step 1 should be 0. Yes. And at 2, it's 0 still. Yes. At 3, it should be 1. Yeah. And let's also try plotting them. I guess visualization is a better way. So we're going to create an array of indices, new int maybe 100, and double step 0 vals, new double indices dot length, double step 1 vals, new double indices dot length, and then for int I equals 0, I less than indices dot length I plus plus, we're going to say that indices I is equal to I, and so what we are going to do, we are going to plot from, let's say, minus 50 to 50. Okay, so 101 minus 50 to length over 2 plus 1 I plus plus, and okay, and then step 0 vals at I. Okay, so no, so we have to stay with that length, but I'm going to just reduce the index. Step val at I equals to step 0 dot evaluate at indices I, and step 1 vals at I is step 1 dot evaluate at indices I. All right, and then the rest is just creating a MATLAB chart, fig new MATLAB chart, fig dot plot indices and step 0 vals. Now this complains because the plot is defined just for doubles, so let's just do double. There is no harm in that. Okay, this says that okay, we can do just so indices is double, so this integer is changed to double, and we can cast it to long, shouldn't matter, and then fig dot plot indices and step 1 vals. Let's plot this with blue color, this one with red color, and then fig dot render plot, fig dot marker on, fig dot show. Okay, it doesn't create the plot because I'm on Mac operating system, so I have to go to the VM arguments and remove this check mark. Okay, as you can see, we have the 0 to 1, and then at the unit step, which has been shifted by 3, gives us 1 at 3, and before 3 index 3 it's 0. Okay, and the unit step, the original one is 1 at 0 and after that, so this is the unit step. All right, let's go back to the PowerPoint and the convolution sum. So the convolution sum is also a very interesting and a very useful thing to implement. So if we have two sequences an and bn, we can define a convolution sum. Now here the assumption obviously is that the sequences start from 0 or 1, so there is no negative index. So here the assumption is that no negative index, which means that for the negative indices we're going to assume that the sequence is 0. Okay, so we're going to just define the convolution from 0 to infinity or 1 to infinity, and then because we're assuming that there is no negative thing, so m is the variable of summation, so the convolution is am bn minus m, and m goes basically from 0 to infinity. And here because b also is a sequence that is 0 for index less than 0, negative index, m is limited to the maximum of n. That's why this sigma is running from 0 or 1 to n. Okay, So we have to take two sequences. If I'm convolving one sequence with another, I have to create a partial sum and then sum them up from 0, 1 to n, okay? Because again, the assumption here is that there is no negative index, which means that an is 0 for n less than 0, or less than or equal to 0, depends on how we define the sequence, and bn is also 0 for n less than 0. Okay, and then the way I'm going to implement it, very simple. This is just a partial sum, right? The sequence is the sum. So here I'm going to create a method called okay, let's maybe move this shift to the bottom here, and then we have another default sequence. Remember, convolution also should return a sequence, convolve. And in the convolve, I'm going to pass another sequence, bn, or b. So we're taking this sequence, which is a, and then convolving it with b. And what I'm going to do, I'm going to return a basically a new sequence using lambda expression called the series object, and the sum, the static method sum, it takes a sequence, all right, and then initial, let's say 0, and last it should be n. Okay, now what we need to do, we need to define this sequence. So sequence sec is this. Basically n or k goes to actually we should do it just here inside the lambda expression so that we have access to this n. So here m is the index of this sequence, inside sequence, which is this dot evaluate. Okay, we do not have access to that, so let's create a sequence a, which is this sequence, and then a dot evaluate. Okay, we still don't have access to this. We want to sum this up with a dot evaluate at n at m, all right, or just maybe okay, times b dot evaluate at n minus m. All right, so we make a copy of this sequence a, and then this returns a convolved by b, so returns a convolution by b. Okay, maybe a convolve a and b. So it takes the summation a evaluate at m, b evaluate at n minus m, and sums it up from 0 to n. All right, now let's go and test it. So let's create a new test, test 4, and public static void test 4. Now what the simple cases that we already know is that if I take a delta of n and convolve it by any sequence an, I should get an, right? So that's the basic thing. Convolution of any sequence with delta sequence is delta is the original sequence. So delta is the identity function or identity sequence for the convolution. So let's test that. let's create a new sequence, delta, and sequence delta at 0, and then sequence A, or sequence A is basically n goes to, let's say an is just 2n, 2 double 2n, okay? And sequence conv A is basically sec A convolve with delta. And what we're going to do, we're going to just plot. So we're going to do sec A and conv A. So sec A is the blue curve and conv A is a red curve. And as you can see, so one thing is that my assumption here is that the A should not be so we define the convolve assuming that it's basically the sequences that we're dealing with are 0 for less than 0. So what I'm going to do, I actually have to multiply this by sequence dot unit step. Okay? Or basically I create this, so this lambda expression returns a sequence and then sequence dot unit step. Must be a functional interface. Okay, let's see. This is our sequence A, and then sec A we want to multiply it by sequence dot unit step. So we make sure that the A is zero for negative index. Okay, now it's 0 and the convolution is basically the same thing. Let's see what happens if we set delta to delta n minus 2. So if I convolve a sequence by delta n minus 2, I should get a n minus 2. So shifting delta and then putting into the convolution actually shifts the the original sequence. So delta by 2, and then the original sequence starts from 0, and then let's see what happens. Okay, as you can see, we're getting a delay of 2. All right, and maybe a fancier thing to say, let's say instead of having a linear thing, let's say we have a maybe quadratic thing, plus 1. So at 0 we are 1, and then we get a delay of 2. So we are 0 until so the original sequence is 0 at -1 and is 1 at 0, and then we shift it by 2 indices, so it's 0 until 1 and then becomes 1 at 2. All right, so it's shifted exactly by 2 indices, 48 and 50. So the convolution seems to work, but let's try to do another test. So we know that, if you recall from our discussion on the polynomials, we said that if you take a polynomial x and multiply it by another polynomial, the coefficients, let's call this r of x, the coefficient Rn is basically the convolution of Pn and qn. So if we take two polynomials and multiply them, basically what it means is that the coefficient of n index for the multiplication, the result is the convolution of the coefficients of the two polynomials. And we can test this using this approach, public static void test 5. So here what I'm going to do, so let's go and invoke test 5. And what we're going to do, I'm going to create a sequence. So let's say our polynomials p of x is just x plus 1, q of x is x2 minus 1, or just x2. So let's see, let's try the polynomial route first. So p is basically new polynomial, and then coefs are 1 and 1. So this gives us x 1 plus x. And then I have another polynomial, q, new polynomial. It's 0 plus 0x plus 1x squared. Okay? And then polynomial r is p times q. Note that the operator is already overloaded. So sys out p equals plus p, sys out q equals plus q, and then sys out r equals plus r. So 1 plus x, 1x plus 1, x2, it gives us x cubed plus x squared plus 0x plus 0. So we get x cubed plus x squared, okay? Which is what we expect. Now using sequences, let's see. So what we're going to do here is I'm going to create a sequence. Let's call this sec p, and this is going to be let's create the sequence delta first. Delta is sequence dot delta. I'm just going to create it using delta. So this is going to be, actually let's do this. Let's try to create a sequence by passing in an array. So let's say default sequence for array, and then we pass in a double array, a 1D array, okay? Then return n goes to basically double array. So we're going to int length is array dot length, okay? And then if n between 0 and length minus 1, so we're going to do this. We're going to say that if n basically n greater than or equal to 0 and n less than array dot length, if this happens basically return array at index n, else return 0, okay? Now this complains because n is supposed to be long, so we're just going to cast it to int. So this is a multi-line lambda expression, okay? So we create a sequence for array, and here it is guaranteed that the index starts from 0 and goes up. So let's do that. So what I'm going to do is that and this has to be a static method, all right? So sequence for array, and we can do a vararg actually. One and one. So this is sec p, and then sec q for array 0, 0, 1. All right, and then sequence sec r is sec p convol by sec q, and then we're going to basically sys out sec p dot basically evaluate at 0, evaluate at 1, at 2, and 1, at 2, at -1, and at 3. All right, so let's do this. So let's here do a sys out. Actually, okay, so let's put this here. So I'm evaluating p. So p is 1, 1. So at -1 is 0, at 1 is, at 0 is 1, at 1 is 1, at 2 is 0, at 3 is 0, exactly like the coefficients here. And now we're going to create, we're going to print basically, let's say printing p, and now printing q, sec q. Okay, all right, so q at -1 is 0, at 0 is 0, at 1 is 0, at 2 is 1. So it's exactly like the coefficient of the x squared. All right, now finally what we're going to do, we're going to print the results of the convolution, printing convolution, or r. So sec r. And let's go up to 5. So what we expect to see for the convolution result is to have basically the third index and the second index. So all right, this is -1, 0, 1, 2, and 3. 2 and 3 are 1, 4 and 5 are 0, 2 and 3. So the coefficient of x squared is 1, the coefficient of x cubed is 1, right? So the convolution of the sequences is exactly the same as multiplying the polynomials. And we can change, we can approve it by changing the coefficients. For example, 2. So we have 2x plus 1 and x squared. So the result is 2x cubed plus x squared. Let's see, 2x cubed plus x squared, exactly like that. Okay, so the polynomial convolution is the polynomial multiplication is exactly the same as sequence convolution. All right, the thing is that for polynomials, the polynomials start from 0. It means when we represent a polynomial by sequence, that sequence is 0 for negative n. It only starts from 0, 1, 2, and etc. Okay, so that's the main thing. So the last thing here is the running average. So the running average is, sometimes we use this in discrete signal processing so this acts as a low pass filter. So it reduces high, very fast changes in the terms of the sequence. So in order to implement the running average, what I'm going to do, again, you can guess, it's a partial sum. So m is the order of the running average. So and it returns a new sequence. So what I'm going to do, I'm going to go to sequence here, use a default access running, or maybe a static sequence running average, and we pass in a sequence, and then return n goes to we pass in a sequence and then int m, or order, and this goes to 1 over order times we call the series class, and the sum we pass in our sequence, and we're going to sum it from n to n plus order minus 1. All right, and then we can have a non-static part for this, and this just takes the order, and this sequence becomes this. All right, so it takes this and applies the running average and then returns the sequence. So let's test that too. So test 6 is going to be testing the running average, test 6, and in the test 6 I'm just going to create a public static void test 6. All right, so I'm going to create a sequence that I know is very sharp. So sequence 6 sec1 is n goes to basically unit step. Sequence dot, all right, just sequence unit step at 0. So this is a very sharp sequence, right? At 0 it suddenly jumps to 1. But let's say that now we try to apply a running sequence. So sec2 is sec1 dot running average with 10, with an order of 10. We're going to filter it. So let's see what happens if we plot it. Step 0, this refactor rename, this is going to be sec1 vals, and refactor rename, this is going to be sec2 vals. So sec1, sec2. All right, as you can see, what happens in the running average is that it adds a ramp. So it removes some of the sharpness, and it adds a ramp to the running to the original step. Okay, so instead of going sharp to like this up, we start smoothly. Now obviously this is the indices are apart, that's why you don't see the smooth transition, you see this ramp one. But as we can see, there is some removal of the sharp behavior of the function. So if I set to -10, it actually goes down. So let's say 220. You see the ramp gets larger and larger. That means it removes some of the it removes more and more of the sharp behavior of the original signal. This was an introduction to how to implement some of the useful sequence operations, and I believe at the moment we have all the tools that we need to really get into more interesting stuff with sequences. So we have looked at the sequence accelerators, we have very powerful operator overloadings, and some of these useful convolution and averaging of the sequences. So we should be able to really start doing or implementing any discrete signal processing system, any system based on discrete signals. And we will look at these concepts in the next lecture. So stay tuned. Thank you for watching, and I'll see you in the next one.